So we're charging objects in one of two ways, charging by induction or charging by conduction. Remember the fundamental difference, the main difference, the one overriding, this works every single time, difference between conduction and induction. Charge transfer, right. We always have a charge transfer with conduction. We always have a charge transfer with conduction. We never have a charge transfer with induction. Now, conduction usually involves touching as well. Induction never involves touching. But again, the overriding factor is charge transferred or not. And by the way, if charge is transferred, it's going to be what that transfers, protons or electrons. Yeah, it's going to be electrons. Protons aren't going to transfer because they're pretty tightly bound in that nucleus by that strong nuclear force. All right, we break conduction down sometimes into two subcategories, charging by friction. We rub two things together. Okay, one becomes, they were both neutral. One becomes +5, the other becomes -5, right? If we had zero charge before we rub them together, and after we rub them together, we must have zero charge as well. +5 and -5 adds up to give me 0. If we charge two things by contact, which sometimes is just called conduction, then it means that we're touching two things together that are unequal charge. One of them is +5, one of them is +7. They're going to try to balance out to be somebody said it, +6 and +6, right? In both cases, we determine the charge on both objects after the touching or after the rubbing by the law of what? Conservation of charge. Principle number 7, the law of conservation of charge. That dictated what the final charge was going to be, whether we rub two things together or simply touch two things together. Now, charging by induction, this is the trickier one. With charging by induction, we can induce that temporary separation of charge, or we can make it permanent. Let's draw a couple pictures here, showing first the temporary separation and then how to make it permanent. Here's a neutral object. Okay, 3 positives, 3 negatives. 3 million positives, 3 million negatives. Doesn't matter, equal number of positives and negatives. Let's bring a positive object nearby. This is different. Last couple times we did this, we drew it on the other side, right? It doesn't matter, right? It doesn't matter where it is. Okay, what's going to happen to the protons in this neutral object if I bring this positive nearby? Nothing. What's going to happen to the electrons? Yeah, they're going to be pulled to the left side. They're going to be attracted to this positively charged object. So we're going to get some electrons over here. I always draw it as if they all go over there, but as you know, they wouldn't all go over there. But it does leave us with one side that has more negative than positive, and one side that has more positive than negative. That's what we call our separation of charge. But it's temporary. It's temporary because Yeah, once I take this away, it's just going to go back to the way that it was before. There's no reason for the electrons to stay separated on one side. All right? Now, you notice that this charging object is closest to the negative side of the neutral object. A positive object is close to the negative side of the neutral object. That's going to mean what's going to happen to these two objects? This positive object is going to do what to this neutral object? Attract it. Positive objects attract neutral objects. Yep. Okay. Yes. Good question. If the electrons jump, that's a completely different thing now. As much as that is possible in this scenario, when I draw this out, we assume that they're not jumping. But if they do, and that can happen when two things get close enough, you know, when you're walking across that carpet and you go to touch somebody, sometimes the electrons jump before you actually touch. We talked about lightning forming, right? The electrons jumping to the ground from the cloud when they're not actually touching. Sometimes that'll happen. If the electrons do jump, first of all, which way are they going to jump? From the positive to the neutral or from the neutral to the positive? They'll jump from the neutral to the positive. Okay? The idea is that the neutral will lose electrons and that'll become more positive. The one that was positive will become less positive. Right? So they'll both balance out, or try to balance out to be positive and positive. So if electrons would jump, okay, if electrons jump, they would jump this way. Okay, that's not what we're trying to show here. We're assuming they're not jumping. But if they did, they would jump this way. And that would no longer be induction. That would be conduction. Okay, it would actually be charging by contact, despite the fact that they're not actually touching. Does that make sense? So a completely different thing if charges jump. We're assuming in this diagram that the charges aren't jumping. All right, we draw one more here where we have, let's go this time, a neutral object, and let's draw our negatively charged object down here. It doesn't really matter, right? It's the same logic that we follow no matter where we draw our object. What's going to happen to the protons in my neutral object? Aaron, what's going to happen to the protons in there? Nope. They're going to stay where they are. They're going to stay where they are. And what's going to happen to the electrons? They're going to move away, right? They're going to be repelled. They're going to be pushed away like this. That leaves us with one side that is negative or overall negative, and then one side that is overall positive. Notice the near side, the side of the neutral object that's closest to the charging object, is opposite. So the negative object is going to do what to this neutral object? It's going to attract it. Charged objects attract neutral objects. Okay, now finally, how do we make it permanent? Ground it, right? We ground it. We can attach a ground wire really wherever we want. Okay, let's put our ground wire right here. Okay, in the end, it doesn't matter where we put it. Okay, what's going to happen? Nothing happens to the protons, right? I've asked that question enough times. We know nothing's going to happen to the protons. What's going to happen to the electrons? Well, this positive object pulls electrons towards it, right? So it's going to suck electrons up from the ground. Now we're going to get a whole bunch of extra electrons. Now we've got a negatively charged object, not a neutral object, but a negatively charged object. If I cut the ground wire, then those electrons will more or less stay where they are and now make a negatively charged object, permanent negatively charged object, right? Now over here, let's ground this one as well. But let's ground this one by touching it against some big object. What's the difference? Zero. This big object basically acts as the Earth. There's a connection between the object right here and the Earth. That's a ground wire. There's a connection between the object right here and some big object that's acting as the Earth. So what happens? If you got a negatively charged object down here, it's going to push the negatives away as far away as we can go. So the electrons are going to go into here. And as the electrons go into here, that makes my formerly neutral object, it makes it positive. Now, if I want to make this permanent, then I separate these two things, and then it's permanently positive. Make sense? All right. We're going to apply what we just did, like we did on Friday to an electrostatic precipitator. We applied it to electrostatic painting. We're going to apply it to another situation right now, what's called an electroscope. An electroscope is just something that detects charge. That's it. It doesn't tell us how much charge we have. It doesn't tell us what type of charge we have, positive or negative. It just tells us if we have charge or not. There is charge here, there is not charge here. Now, how does this work? We have electroscopes back there. I'd show you if it actually, on our electroscopes, worked well, but we just have like the cheapo electroscopes. They would be like the equivalent of dollar store electroscopes if you could buy them if you could buy electroscopes at dollar store. It just doesn't work. So it's not going to, there's no point in hauling them out and showing you. It consists of, this electroscope, this charge detector, consists of a little metal ball, okay, a steel ball right here. And connected to that steel ball will be this steel rod, this metal rod. And then connected to that will be, well, you could have two little leaves, two little foil leaves, or you could have, sometimes it's two little pith balls, it's called. Two little things about the size of a pea. Pith is from a material from the interior of a plant, and if it's coated with a metallic coating, then it can work really well in electrostatics experiments because it's light, but yet a conductor. Okay, does that make sense? Usually we end up seeing these two leaves, though, as opposed to the two little pith balls. Now, you see two different versions of this, basically the same thing, right? Metal ball, rod, two little leaves, just what surrounds it, right? We like to surround it with something because that keeps air currents away from this to affect it. And these leaves are pretty susceptible to air currents because they're so light, so thin. If you think of aluminum foil, way too heavy, way too thick, way too heavy. Okay, we're talking about foil that is way, way thinner and way, way lighter than aluminum foil would be. Okay, now so how does this detect charge? Let's bring a negatively charged object nearby. And let's assume that before we do that, there was an equal number of protons and electrons in this electroscope. Got it? And they're evenly distributed, pretty much, at least evenly distributed, right? What's going to happen when I bring this negatively charged object nearby? What's going to happen to the protons? Ryan, what's going to happen to the protons in that electroscope? Nothing. Nothing. That's always the answer, by the way. If I ever ask that of you, it's not a trick question. The answer is nothing. Okay. What's going to happen to the electrons? They're going to move, right? Where are they going to move? They're going to be pushed down into the leaves. They're going to be pulled up. They're going to be pushed down. Yeah. Again, probably not all of them, right? But you're going to get lots of them pushed down. Okay. Notice what that does. That causes, first of all, the ball of this electroscope to become positive, right? And it causes this leaf to become negative, and it causes this leaf to become negative. What happens to these two leaves if they're both negative? They repel each other. Good. They push each other apart. So now, instead of these two leaves coming down and being close together, now these two leaves end up pushing each other apart, spreading apart. We've just detected charge. We know there must have been charge present in this thing that I brought nearby. You know, you bring this rod nearby, you can't see these. You can't see whether it's negative or positive or neutral. Okay, but now we know that there was charge because the leaves spread apart. Does that make sense? Okay, let's take a look at the other one if I was to bring a positively charged object nearby. Again, we can't see the positive. We don't know that it's positive. We just know that it's some object, some rod that we're bringing nearby. This was neutral. We had an equal number of protons and electrons, pretty much evenly spread out. What's going to happen to the protons in this? Caitlin, what's going to happen to the protons? Nothing. Good. Sarah, what do you think is going to happen to the electrons? They're going to go, yes, they're going to go up. Good. They're attracted to the positive, right? Whoops. We didn't want it that big. And again, not necessarily all of them will go up, but lots of them will go up. So let's draw it as if they all go up. That leaves the ball of the electroscope negatively charged, and that leaves this leaf positive, and that leaves this leaf positive. What's going to happen to the two leaves if they're both positive? Kevis, what's going to happen to the two leaves if they're both positively charged? They'll repel each other, and therefore they're going to spread apart. So we're going to get the exact same effect as we got over here. The leaves spread apart. Make sense? So you can see here that we've detected charge, whether we bring positive or negative nearby, you detect charge in this electroscope. But you can also see that we get the exact same effect in these leaves, whether it is positive or whether it is negative. It detects charge. It doesn't tell us how much charge or what type of charge we have, just that there's charge present. Okay, let's do one more thing here. Well, one more thing on each of the diagrams. Let's ground it. Does it matter what side I ground it on? No, No, if I ground it, I ground it, right? I could bring another big object nearby and touch it as opposed to attaching a wire literally to the ground. Whatever, same thing. What do you think is going to happen now? This wants to push negatives down into the ground, right? Well, actually, it wants to push negatives as far away as it can push them. Now, as far away as it could push them was down into the leaves. That's not the case anymore. Now, the furthest it can push them is down into the ground. So now, what happens? Do these leaves come back together? They were negatively charged and spread apart like this. Okay, do they come back together like this, Sean? No, why not? Because now they're both positive. Now they're going to be spread apart because they're positive, right? Now, what do you think is going to happen? What about this? What do you think is going to happen if I cut that ground wire now? The leaves are now spread apart, right, because they're both positive. Cut the ground wire, what's going to happen? They're going to come back together? No. There's no way for the leaves to come back together until they absorb electrons from the air or something, right? Because they're positively charged and they can't get a negative charge, or they can't get a neutral charge anymore. Make sense? So they're spread apart, and now it's we say it's permanent. It's not really permanent, right? They're not going to stay spread apart forever. Like eventually electrons will come in from the air and it'll absorb electrons from the air, but they'll stay apart for a while at least. We say it's permanent here. You had a question, Nolan? Yes, they would. Yeah, but it's we think of an analogy here. Like in the end, if I don't know if this is a good one or not, but we'll try it. Yeah, I've got a bucket here, let's say, and there's water in the bucket, and I put a hose right here. Okay, I put a hose in the bucket right here. Okay. Sometimes what I can do, if the hose isn't under high pressure, then it'll just fill up the water, and the water will just fill up, right? But if the hose is under a fairly high pressure, what happens is this water can sometimes, you can sometimes push this water that was down here kind of up and out of the bucket. Does that make sense? And that water has to get closer to the water to this water that's being forced in. So you're pushing water down, but because of the pressure, it kind of gets pushed out and it has to come back up there past that in the process. Does that make sense? So you got a similar thing. You have a similar thing going on there. Those electrons would have to go past there, but they're being pushed down and pushed out of there. Is that I don't know if that's a good analogy or not, but okay. I don't know how hard it is to actually, depends on the size of the bucket, I guess, but you can imagine at least how that could work. Okay, let's take a look at the last one here. What if we attach a ground wire to this? Let's make it on the other side, though. Let's make it on this side. It doesn't really matter, right? What's going to happen to this one? Well, what's going to happen to the protons? What's going to happen to the protons? Nothing. What's going to happen to the electrons? We want to get electrons. This is positive, right? We pull the electrons from as far away as we can. So we're actually going to pull electrons up from the ground. Okay, now you're going to get some of those electrons draining down because they're not all going to hang out up here, right? At some point, you're going to have too many electrons up here, and then they're going to start pushing each other away. So some of them will come down here. You're going to get more up here because it's close to this, but you're going to get some of them filtering down there. What happens to the leaves? Well, they were positive, but now you got a bunch of electrons in the mix, so now they become negative. So now the leaves spread apart because they're negative. And if I cut that ground wire, then they're permanently negative. Permanently, I say that with quotation marks, permanently negatively charged. Make sense?